Hello, good morning everyone. We are the students of IIT Kanpur, Mtech Computer Science, and we are going to present a review about paper called DEJA VU, Continual Model Generalization for Unseen Domains. This is the presentation by Group 1. Let's have the brief introduction. Deep learning models struggle to maintain performance during significant data distribution shifts, especially in the unfamiliar period when encountering new or unseen environments. Existing domain adaptation and generalization methods are limited by poor performance during sudden shifts, reliance on source data, and catastrophic forgetting of learned domains. The proposed RATP framework aims to enhance model performance during the unfamiliar period. This work addresses the continual domain shift learning CDSL problem. The proposed RATP framework focuses on the three key objectives. These are the objectives. First one is target domain generalization TDG. It enhances performance before and during the training on unseen domains. Second one is target domain adaptation. It ensures strong performance immediately after the training. And third one is forgetting elevation. It maintains performance on previously trained domains. Basically, RATP first starts with a labeled source domain. It applies rand mix on the full set of source data to generate augmentation data, and it uses a simplified version of PCA for model optimization. Then, for continually arriving target domains, RATP uses T2PL to generate pseudo labels for all unlabeled samples. It applies rand mix on a top subset of these samples based on their softmax confidence, and at last it optimizes the model by PCA. So let's have a look on RATP components. The first one is a random mix-up, a training free data augmentation method to improve generalization. Second one is top to pseudo labeling T2PL. It produces accurate pseudo labels by prioritizing confidently classified samples. And third one is prototype contrastive alignment PCA. Let's see the first component, random mix-up augmentation. Basically, random mix is introduced to improve cross-domain generalization when the model is trained on a single label source domain but tested on unseen target domains. It serves the purpose of enhancing the model's ability to generalize across domains and remain agnostic to domain order, especially for low-quality target domains. Here, random mix uses autoencoders initialized with random parameters to generate augmented data. Basically, noise is injected using ADA-in, adaptive instance normalization, to introduce controlled randomness and prevent degradation for generalization, basically to avoid overfitting. Training data is fed through the autoencoders, then it's summarized and scaled by sigmoid function. The sigmoid function is the standard function which bounds the output of the function between 0 and 1. Then specifically we determine whether a target sample is supposed to be augmented based on its prediction confidence given below. Then next component is top to pseudo labeling. CDSL requires a pseudo labeling mechanism for accurate supervision in target domains. T2PL has four main features: confidence based selection, centroid refinement, then k nearest neighbor classifier, and top selection strategy. Basically, top to pseudo labeling T2PL improves pseudo labeling accuracy using softmax confidence, and then T2PL employs KNN to assign pseudo labels, reducing misclassification risk effectively. It selects only the top 5% of samples for each class to improve labeling precision. Next one is prototype contrastive alignment PCA. It is a domain specific. Prototypes are typically constructed by aggregating class samples. However, when these prototypes are misaligned, they can create an adaptive gap. So PCA algorithm is introduced to address this gap by using a more robust alignment strategy. Prototype learning effectively addresses cross-domain sample variability and sample insufficiency issues. Prototypes PX are obtained by cross-entropy loss, which is the standard loss of classification problems. The algorithm incorporates contrastive comparison to enhance class distinguishability in alignment. The final loss function combines cross-entropy loss, PCA loss, and distillation loss. By applying PCA, the model can better align domains, reducing the adaptivity gap, improving generalization, and maintaining performance on previously learned domains. Then we will conclude the review. The paper addresses model performance during the unfamiliar period of continual domains. A novel framework called RATP is proposed to tackle this challenge effectively. RATP incorporates training-free data augmentation, pseudo-labeling, and prototype contrastive alignment. Extensive experiments show RATP outperforms the state-of-the-art methods in various domains. Thank you.